Yes. Thing back. Oh. It's fine.
Okay, thank you all. So thank you for coming today. I wanted to start off by just kind of saying a little bit of background about myself. So currently work on algebra and number theory, but back n number of years ago, where n is a number, I was a grad student, and when I was a grad student, I was studying model theory, which is a branch of logic, and I was interested in how model theory related to algebra. And it's a really neat subject. It's a very powerful subject. And I kind of looked through your course catalog before coming here, and I saw that I don't think that there's any course beyond your intro to proofs course where you see any sort of logic, and especially any logic that really is powerful for working with other fields of math. So I wanted to teach you some of that so that you see that actually logic is quite a powerful tool for solving a lot of problems. The talk is going to be split into 3 pieces. So should it be projected over here, Jim? On screen?
Oh.
It's going to be in 3 pieces. The first part is I'm going to give you a crash course in model theory, just enough that you're able to understand what I'm going to do later. And then I'm going to have 2 applications. One is going to be to combinatorics, to something called Ramsey theory, and another one is algebra/analysis in something called axis theory. Great. So when you're in math, you typically study an object, and it looks like something like this. So I've got S, F1, R1, C1. So S is a set. The CIs are constants, so those are special elements of our set. So things that specific elements that we really care about and want to give names to. It's getting cut off. Okay. The RIs are relations. Okay, so what is a relation? It's going to be each RI will be a relation relating k elements of S together. So like a binary relation will be relating pairs of elements, a ternary relation will be relating triples of elements. And so we're going to have relations that relate certain tuples of elements together. And those tuples, the number of elements in each relation could vary as we go from relation to relation. And then control minus, it might control minus. Thank you. Oh yeah. Okay, great. No, it's still too big.
I've heard
yeah, this looks good. Okay. And then we've got functions, F1 through F, however many functions that we have. And each one is going to have, it could just have one input, or it could have n inputs. So I want to allow for all sorts of possibilities. The inputs are coming from our set S, and the output is also in S. So let me do a quick example. Okay, so here is the integers. And so our set S is the integers. There's 2 very important integers that we want to have names for, 0 and 1. There's a nice binary relation on the integers, less than or equal. So this is a relation that relates pairs of elements to each other. X1 is less than or equal to X2. And then I've also created 3 functions here, addition, multiplication. Both of those take pairs of integers and give an output, either the sum or the product. And then minus, I could have done subtraction here, but just to change things up, minus is actually negation. So it has an input of 1 integer, not 2, because it takes each integer to its negative. Okay, so this is an example of a type of set. I just wanted to give something where you kind of see, okay, what are functions, what are relations, what are constants? Okay, so when we're studying this object, we've got names for the functions, the relations, and the constants. Then we want to say what those objects are supposed to do. So we're going to have logical formulas, statements that are going to say, these functions have to do that, these constants have to do that. Okay, so when we're creating these formulas, we're allowed to use any of these function symbols that we've created. The functions, the relations, the constants. We're also allowed to use variables, xi, to represent the elements of S. And then we're allowed to combine things using logical connectives, things like the equal sign, and, or, negation, implies, if and only if. And lastly, we're allowed to use quantifiers. We're allowed to say for all and there exists. So, okay, here's an example of a statement that we might have. So statement 1 is a statement about one of the functions, f5. Anyone want to say what that statement is saying about f5?
Injective.
Yeah, it says f5 is injective, right? Every time f of x1 equals f of x2, that means that x1 equals x2. That means that the function is injective. Here's another one. It's saying a statement about the relation R1. Anyone? Yeah, well, okay, so relation, you're not commuting, it's symmetric, right? So if this was a function, you would say it commutes. If it was a relation, you say it's symmetric. Okay. And then the last one was just a silly one that I just made up. It says that there's an element that's related to every other pair of elements, x2 and x3. Okay. All right, so I do have some warnings here about what you can do with these formulas. Okay. The first one is that a formula is a finite string of symbols. Okay. So you are not allowed to use infinitely many variables. You are not allowed to use infinite disjunctions. You're not allowed to have infinitely many quantifiers. So that means saying something like x is some nth root of 2. You cannot say, oh, x is 2, or x squared is 2, or x cubed is 2, or dot, dot, dot. Okay, that's an infinite disjunction. It's not allowed. Okay. All right, that's not too surprising. The next thing is a little harder to resist, which is that your variables are only coming from the set S. So that means when we're writing a formula, we're not allowed to have a quantifier like for all epsilon greater than 0, or a quantifier like there exists a natural number, because those variables are coming from outside of S, they're coming from N or from the reals. Okay, so you're not allowed to use quantifiers from the natural numbers or from the reals, unless, of course, S was natural numbers or the reals. In particular, it's really hard to say there is a finite subset of unspecified size that does something. Okay, you're not really allowed to say that. The last thing is that the variables are elements of the set. Okay, not subsets of the set, not collections. So you are not allowed to talk about things like ideals or topologies or anything like that. Okay, and that's a real kind of a letdown, because a lot of mathematics you do talk about not just the elements of your sets, but also subsets of your sets. So it might seem like I'm being way too restrictive here, and I'm missing a lot of the expressive power of what we're talking about in mathematics normally. But having these restrictions actually make us stay within first order logic. And within first order logic, that's where we have the most powerful theorems that are the most applicable across mathematics. So it is good to stay to keep these restrictions in mind. Even though I have these restrictions, there are some workarounds around some of these. So for example, so this is just kind of motivating the next thing. How would you say that the set S has at least 2 elements? What formula would you write there?
There's this x1, there's this x2 such that x1 is not equal to x2.
Exactly, right? So it's not enough to just say there exists x1, there exists x2, because that just, those could be the same element, so we want to actually say x1 is not equal to x2, right? There exists x1, there exists x2, x1 is not equal to x2. Now, if you want to say S has at least 3 elements, well, you'd say there exists x1, there exists x2, there exists x3, and then you actually have to say every possible combination, they're not equal to each other in order to say that they're all distinct. Okay, and this is because not equals is not transitive or symmetric, so where it's not transitive, so you actually have to go through all the combinations. How do you say there's at least k elements? Well, it's k quantifiers, existential quantifiers, and then all possible pairings, xi and xj, you have to say that they're distinct. Okay. So how do you say that S has infinitely many elements? Well, kind of seems like I need to have infinitely many quantifiers, right? But there's a workaround. And the workaround is, look at each one of these formulas that we just created that said you had at least k different elements. S is infinite if all of these formulas are true, right? So for each k, S has at least k elements. And as I run through all k's, I've forced S to be infinite. So even though I'm not allowed to have a quantifier over the natural numbers, a lot of times when you have a for all natural numbers, you can just turn that into infinitely many formulas that S has to satisfy. Okay. So my formulas are finite. I only got finitely many variables, but I'm allowed to say S has to satisfy infinitely many formulas. All right. Any questions so far? Okay, great. So this is the key idea here is now I've got a set of formulas, T, that might be a finite or an infinite set. And we're going to say T has a model if I can find some set, some functions, relations, constants, that make every formula in T simultaneously true. All right, so here's an example of theory T. It's going to have these mu sub k's, so these formulas that said I have at least k distinct elements, and then 2 additional formulas, P and C. Okay, I'm working with a function and a constant, and phi is saying for all x1, f of x1, x2 is f of x2, x1, as you said, that's commutative. And C is saying for all x1, if you do f with the constant in x1, you get x1. Okay. So in order to make T true, in order to be a model of T, you have to have at least k elements for every k. In other words, you have to be infinite, and you have to make this and this true. And there's lots of possibilities for that. So you could do the integers, make your function plus, and make your constant 0. Or you could do the reals and make your function times and make your constant 1. Okay. Those are just 2 possibilities. All right, so here's the big theorem from model theory that we're going to use today. It's called the compactness theorem. It says if I've got an infinite set of formulas, that infinite set of formulas has a model that can be made simultaneously true if and only if every finite subset T prime of T has a model. As a tool, this is saying I have some infinite set of formulas. I want to say they are consistent. I can find some set and functions and relations that make them all true simultaneously. By compactness, all I have to do is look at every possible finite subset and make all of those finite subsets individually true. And that's a much easier problem because I've only got finitely many sentences at any time, finitely many formulas to make it true. I do have to consider all possibilities, but just having finitely many formulas is a lot easier to work with. All right, so we're going to use this compactness theorem in 2 settings, Ramsey theory and axis theorem. So Ramsey theory, is about graphs. So a graph is a set of vertices along with edges between those vertices, so connections between those vertices. And we don't have to connect all the vertices, we just can connect some of them. So for instance, if we had 3 vertices, these are all the possible graphs on 3 vertices. This one up here has no edges between any of the points. This one down here has edges between all 3 points. And then you've got combinations that are 1 edge or 2 edge. How would you characterize graphs using logic? Well, a graph is really a set V of vertices, along with a binary relation called the edge relation. And the edge relation just has to satisfy 2 things. First off, if I've got an edge going from x1 to x2, that really is an edge from x2 to x1, right? I don't have an order here. I've got an edge from A to B, that's also an edge from B to A. Okay. So for every pair, I have that true. And then the second part of that says, for every point x3, I do not have an edge from x3 back to itself, right? I'm not allowing loops. Okay, so this gamma is just the defining formula for graphs. And there's 2 graphs that we're going to be really interested in for Ramsey theory. So Kn is the graph on n vertices where you have every possible edge. Okay, so here's an example of K5. 5 vertices, all possible edges between those 5 vertices. Kn bar is the opposite. You have n vertices with no edges between them. So K5 bar, we've got 5 vertices, no edges at all between them. So this is a nice little theorem that you might prove in combinatorics class. It says that if you've got a graph on 6 vertices, no matter how you put down those edges, either you're going to create a copy of K3, so you're going to have 3 vertices in a triangle connected by edges, or you're going to have a copy of K3 bar, meaning that you've got 3 vertices and they have no edges between them. And 6 is the smallest number for that. Okay, if you're doing K3, and you might ask yourself, well, what if I was doing K4? Okay, now I want a square where I've got all possible edges, or 4 vertices with no edges between them. And in general, there's a theorem called the finite Ramsey theorem, which says whichever n I choose, I can pick R much, much bigger than n in practice. And such that every graph on R vertices is going to have somewhere inside it n vertices that are all connected in every possible way, or n vertices that have no connections at all between them. This is called the finite Ramsey theorem. There's also an infinite Ramsey theorem, which says, now let's imagine I had infinitely many vertices. And I created a graph on that. I connected some of the vertices with edges. Well, the infinite Ramsey theorem says, somewhere inside that infinite graph, I've got infinitely many vertices that have all possible edges between them. Or I've got infinitely many vertices that have no edges between them. And I think I have time. So here's the proof. Okay, so let's imagine I've got the vertices, these yellow dots, and they're going off to infinity. And pick the first vertex. Okay, and just pick one at random. Well, it's going to be connected to some of the other vertices, not connected to some of the other ones. And since there's infinitely many other vertices, either this thing is connected to infinitely many other vertices, or it's not connected to infinitely many other vertices. Right? You've got infinitely many things, they're going into 2 buckets. One of those buckets is going to be infinite. So let's say this one is connected to infinitely many vertices. And then I throw away everything that it is not connected to. And I'm going to make this vertex blue. Now. Okay. Then I go to the next vertex that I have not thrown away yet. There's still infinitely many vertices left because I only threw away. When I was throwing things away, I made sure that I had infinitely many things left. This one, similarly, is going to be either connected to infinitely many things or disconnected from infinitely many things. Maybe this one is, so maybe here's a connection, okay, and these two are not connected. And maybe this one is not connected to infinitely many things. So I'm going to throw away everything that it was connected to. And I'm going to color this one red. I keep going down the line. Okay. So the goal, the result of this is that a blue vertex is connected to all vertices to the left. To the right, sorry. Think of it. And a red vertex is connected, not connected to any vertices to the right of it. All vertices. So I go through this process and I've finished at the end. And now I look, okay, I've got infinitely many vertices left. Okay, and they're all colored blue or red. Well, I've got infinitely many vertices, they're colored by two colors. One of those colors has to be infinite. If it's the blue color that's infinite, all the blue vertices are all connected to each other. Because every blue vertex is connected to everything beyond it. So this one, if it was blue, would be connected to everything beyond it. Then I go to this one, it's connected to everything beyond it, but also that blue one by construction. And so all the blue vertices would be a copy of K infinity. If instead the reds were infinite, well, the reds are not connected to anything after it. So if I did all the red vertices, they would not be connected, and that would be my K infinity bar. So that's the proof of infinite Ramsey theorem. It's actually a lot easier than finite Ramsey theorem. And that's great because we're going to use compactness to prove that infinite Ramsey theorem implies finite Ramsey theorem. Okay, so there's the proof of infinite Ramsey. Okay, so proof of finite Ramsey from infinite Ramsey. So let's assume for contradiction that finite Ramsey is false. All right, so let me remind you what finite Ramsey said. It said for each n greater than or equal to 1, there exists an R. So if we negate that, that means there exists an n for all R. All right? So there exists an n greater than or equal to 1, such that for all R, I can find a graph GR on R vertices. And somewhere inside that graph, or inside that graph GR, it has no copies of Kn and no copies of Kn bar. Okay, that would be how Ramsey would fail for this n. All right. So that means actually GR satisfies this formula, capital Phi. Okay, what does this formula say? All right, it says anytime I choose n vertices, if they're all distinct, then among those n vertices, some pair has to have an edge. Right? One of these edge statements has to be true. Also, somewhere among those pairs, one of these edge statements has to be false. So somewhere I have to be missing an edge. Right? That's how, if you're missing an edge, then you're not Kn. If you have an edge, you're not Kn bar. So every time I choose n distinct vertices, at least two of those vertices have an edge between them, and at least two other vertices have no edge between them. In other words, I have no copy of Kn and no copy of Kn bar anytime that I choose n distinct vertices. Well, now let's consider the infinite set of sentences of formulas. I'm going to use that gamma, which was a graph axiom. I'm going to use that phi, this ugly formula from the previous page. And then all those new k's, which said that you had at least k elements. Okay. For any finite subset of T, we can find the model of T prime of that finite subset. Why? That finite subset is going to have maybe gamma, maybe capital phi, but it's only going to have finitely many of the new k's. So it's only going to say that I have to have, at least k elements for finitely many k. So just take R to be that maximum k. And now consider GR. GR is a graph that makes all these new k's true because it has at least k elements for each one of those finitely many k's. It's a graph, so it makes gamma true, and it makes capital phi true because it was the counterexample. So each finite subset T prime has a model, it has a statement that's true. Well, by compactness, that means the whole infinite set has to have a model. So that means I've got a graph G that makes all of these statements true. It's going to be a graph that satisfies gamma. It's going to make capital phi true, which was that funny formula. And it's going to be infinite because it makes all those new k's true. Right? It says I've got at least k elements for every possible k. Right? So G is going to have infinitely many vertices. But then since G satisfies this capital phi, every time I choose n vertices of G, I do not get a copy of Kn or Kn bar. That's a contradiction of infinite Ramsey. Because G is an infinite graph, G has to have a copy of K infinity, infinitely many points that are connected, or infinitely many points that are not connected. In particular, if I've got infinitely many points connected, I should have n points connected. And if I have infinitely many points not connected, I'd have n points not connected. So there's a proof of finite Ramsey from infinite. Any questions about that? Okay, so that was one case where we used compactness. Basically, we only had one formula here that was really interesting, this capital phi. But then we had these formulas mu k that said I have to be at least k elements. I have to get bigger and bigger and bigger. And if I had all of them, that would force me to be infinite. All right, second application is in field theory. So here's the definition of a field. If this is intimidating because you haven't seen fields, wait till the summary and I'll explain. But a field is a set F with addition, multiplication, special elements 0 and 1. And they have to satisfy these axioms, these formulas, which I'm going to call T sub F for field. But basically, the summary of them is that addition, subtraction, multiplication, and division are all possible, and they all work exactly like you're familiar with from the integers, from rationals, and from reals. Okay, so some examples of fields are the rationals, the reals, the complex numbers. You can divide complex numbers. But so are the integers mod p when p is a prime. Okay. Not when p is composite, it has to be for a prime. And what's interesting there is the first three examples are infinite sets. The last one is actually a finite set, so there are finite fields. And kind of one of the reasons for that, well, one of the things that really differentiates these is that in ZP, if you add 1 to itself p times, you get 0. And that's a nice formula that ZP satisfies. But if you were working in Q or R or the complex numbers, then for every n, if you added 1 to itself n times, you would never get 0. Okay. This is called, when this happens, your characteristic p. When this happens, your characteristic 0, because there is no multiple of 1 that gets you 0. There are infinite fields that are characteristic P, and we'll see one in just a minute. But they act very differently than the rationals or the reals do. All right, Axis theorem is something about polynomials, so we do want to talk about polynomials. So what does a polynomial look like? Well, it looks like I've got some coefficients a0 through an. They're coming from my field f. And I multiply them together with powers of x and add them together. And then I could say that an element of f is a root if when you replace x with that r, you get 0. The nice thing is this statement p of r equals 0, that's a logical formula using our symbols, plus, times, and our constants, right? Okay. If you've never taken field theory, or I guess, an abstract algebra course that does fields, you wouldn't know this theorem, but it is a nice theorem, and it says that if I start off with a field, f, and I pick out my favorite polynomial, well, sometimes that polynomial has a root in f. A lot of times it doesn't. And the theorem says, oh, I can enlarge f to some slightly bigger field E, and that field E will have a root of my polynomial. So, example, if I had my favorite polynomials x squared minus 2, and I started off in the rationals, that does not have a root in the rationals, but I can go bigger. In this case, I can go really big, actually. R is overkill. But I can go to the reals, and the reals do have a root, square root of 2. And then if I started off with the reals instead, and I looked at the polynomial x squared plus 1, well, you could go a little bit bigger for the reals. You can go to the complex numbers, and you find that I is in the complex numbers, and that's the root of that polynomial. So we went from Q, we extended it to R, then we extended R to the complex numbers, and you might say, okay, well, should we extend the complex numbers? Should we keep going? Keep going. So are there polynomials over the complex numbers whose roots we need to add to the complex numbers? And spoiler alert, if you've ever taken an algebra course on field theory, this is a major theorem. And I don't think most intro algebra courses ever prove this because it's actually pretty involved. But yeah, it's analytic, I think, right? So it's the fundamental theorem of algebra says that every non-constant polynomial with coefficients from their complex numbers actually has a root in the complex numbers. Okay. So you can express that in terms of logical formulas, which is great. So basically, if I've got my favorite polynomial, an, a1, a0, I'm saying there is a root to that polynomial, so there is an r that makes this 0. This is just multiplications and additions. And then I want to say that's true for all possible choices of my coefficients, right? As long as my leading coefficient is not 0, so I'm actually dealing with polynomial degree n. This formula, phi n, says polynomials of degree n have a root, but I need to run through all possible degrees. So C is a model for all of these phi n's as you run through all the possible values of n, all the possible degrees of the polynomial. C was very special, but it is not the unique field with that property. So if I took my favorite prime P, there is also a countably infinite field, which I'm going to call C sub P, just so you remember that it's like the complex numbers, but it's kind of extending ZP, integers mod P. So it's going to have this funny property that when you add 1 plus 1 plus 1, P times, you get 0. And this CP also has roots for every polynomial, but now the coefficients are coming from CP. Okay, and the root is coming from CP. Okay, so complex numbers is the only real difference I need to remember is that complex numbers 1 plus 1 plus 1. never is 0, but in CP, 1 plus 1 plus 1 is 0 if you do it p times. And both of these have all roots to all polynomials. So let's talk about these polynomials. A basic question that you can ask is, are they injective or surjective? So let's just start off pretty simple. Let's go with f of x is x squared. Well, that's not injective because f of 1 is f of negative 1. It's also not surjective because it's missing all the negative reals. What about if I did x cubed? That one is injective, because to find out what x is, I just take the cube root, and it's surjective. In fact, you can argue that any polynomial of odd degree over the reals, using calculus, you can argue that on one side, as x goes to infinity, we're going to go to infinity or negative infinity, and then as x goes to negative infinity, we'll do the opposite. So we're going to run through all the reals. So that means this function f of x equals x cubed minus 3x is surjective because it's odd degree, so that's using calculus, but it's not injective. So you can check f of 2 equals f of negative 1. Now, so far, I've only been using one variable, but there's nothing stopping me from using multiple variables. So what if I took a function f going from R3 to R3? So 3 inputs, 3 outputs. And what does f do to the 3 inputs? Well, each output is a polynomial of my variables. Well, this one, so according to 1, x1 minus x2, x1 minus x3, x2 plus x3. If you did a little bit of linear algebra, you realize, if I had f of x1, x2, x3 equals f of x1 prime, x2 prime, x3 prime, you can actually do linear algebra, solve those equations, and say, oh yeah, those are the same inputs. So it's injective. And then also, doing some linear algebra, you can show that if I gave you some b1, b2, b3, you can find x1, x2, x3, such that that output is b1, b2, b3. All right, so what else can we do here? We could change some of these to the complex numbers instead of the reals, and actually some things would change, like the first one would be still not be injective, but it would actually be surjective. And we can use multiple variables, things get more complicated. I mean, this was really simple, it's all linear. But if you look at every situation, there's cases where injectivity fails, surjectivity fails, injectivity is true, surjectivity is true. But if you look at all kinds of combinations, there's never a case in this list where you're injective but not surjective. And that's a little curious. And then you try to figure out examples, and you realize I'm having trouble. If I'm going from Rn to Rn, I'm having a lot of trouble coming up with something that's injective but not surjective. And that's because it's impossible. Okay, so this is a theorem of Baginski and Birula and Rosenlicht. So if you've got a function from Rn to Rn, that's a polynomial function in n variables. So you've got n variables as inputs, and each output is a polynomial, and each coordinate is a polynomial in those coordinates, in those variables, right? So each one of these coordinates was a polynomial. So if you've got a polynomial function in n variables, if it is injective, then it has to be surjective. I don't know how to prove this. It's algebraic geometry or tropical geometry or something like that. But I do know how to prove the same statement for the complex numbers. And so this was proven independently by Axe and by Grothendieck. And the proof that I'm going to give you today actually has to use compactness as well. Okay. And this is a really useful theorem because actually you can show a lot of polynomial maps are injective a lot more easily than you can show that they're surjective. So like this polynomial function, which is from C2 to C2, just has two variables. you can show using Jacobians that this is an injective function. That's not too bad. But access theorem now says this has to be a surjective function as well. So if I gave you two target output like 1, 3, you'd have a hard time figuring out probably what x1 and x2 would need to be so that this polynomial turns into 1 and this polynomial turns into 3 simultaneously. Access theorem says it's possible. All right. So access theorem is claiming that complex numbers are a model of this following infinite set of formulas. Okay, so the field axioms, PF. Then these axioms that I've told you about how many times 1 gets added to itself to get 0. We should never get 0 for every value of n. Okay, so that's infinitely many formulas right there. Then these formulas, phi n, we're saying all polynomials of degree n have a root. Okay, so we already talked about those. The new formulas, there's infinitely many, and they're indexed by 2 numbers, n and d. N is the number of variables, and d is the degree of the polynomials. So C and D is saying for all polynomials that we pick, P1 through Pn, that use n variables, and if they have degree at most d. Now if we look at the function, which also is on n variables, where the first coordinate, the output is given by P1, second coordinate, the output is P2, last coordinate, the output is given by Pn. If that function is injective, then it actually has to be surjective. Okay, so this is what access theorem is saying, and access theorem is saying this is true not for a particular n or a particular d, it's true for any n and any d, any number of variables and any degrees for my polynomials. This statement can be expressed in first order logic because polynomial is just a finite string of symbols. The degree here is fixed. The number of variables is fixed. We're doing for all polynomials, so we're quantifying over all of those coefficients. So there's only finitely many coefficients to quantify over. And as we already saw, being injective is expressible in first order logic, and so is being injective. So these are all the statements that we're saying that the complex numbers have to satisfy. And by compactness, all we have to do is show that every finite subset of these statements has a model. So let's look at a finite subset, T prime. Well, it's going to have some of the field axioms, some of the axioms of type 2, some of these axioms of type 3, some of these axioms of type 4. In particular, it's only going to have finitely many of these statements that 1 plus 1 plus 1 is not 0. Okay, so I'll have that for doing a sum of n1 ones, n2 ones, and k ones for some finite number of values of n. So if we pick a prime p greater than all of these numbers, then the complex numbers, the CP, this complex numbers with 1 plus 1 plus 1 equals 0 for sum of p ones, that one will satisfy these formulas because the number of times you had to add 1 was p, and that's bigger than all these n's. And so you're not going to get 1 plus 1 plus 1 3 times is 0. You're not going to get 1 plus 1 plus 1 8 times because the prime that I picked was really, really huge. And now we're going to claim that this CP is actually a model of T prime. Okay. So T prime, again, has finitely many of these axioms of type 1, type 2, type 3, type 4. CP is a field that's going to satisfy everything in type 1, all the field axioms. We already picked P big enough so that the finitely many things of type 2 are all true. And CP has roots to all of its polynomials, so it satisfies all the statements in 3. So all we're left with is these CNDs for different n's and d's. Finally, many of them are going to be in T prime, and we have to prove that CP satisfies. So to remind you what that means, every time we pick n polynomials in n variables that have degree n most d, if that resulting function is injective, then that function also has to be surjective. So we have to prove that this statement is true in CP. All right, so let's take n polynomials and n variables of degree at most d, some random ones that are given to us. And we're going to assume that the resulting function is injective, and our goal is to prove that it's surjective. So that means if we're given some target in CP to the n, b1 through bn, we're going to have to find an input a1 through an, where when you put that input into p, you'll get b1 through bn. Meaning, if you put that input into the first polynomial, you'll get b1, the first coordinate here. Okay? And then if you do that for every other polynomial, you get bi for each other i. So that's our goal. Well, I mentioned some facts about CP, and probably they went by pretty fast. But CP, at least what I stated, was a countably infinite field. And in fact, if you do that construction of adding roots really, really carefully, you can start off with CP, extend it to a finite field, extend it to a finite field, adding roots all the time. And you can actually add all the roots so that CP is actually a union of an increasing chain of finite fields. This is something that is not true about the complex numbers. Complex numbers are not a union of finite fields. Now let's look at those polynomials. P1 is a polynomial. It's got finitely many coefficients. P2 has finitely many coefficients. Pn has finitely many coefficients. And the BIs are also finitely many elements of CP. So at some point, all of those elements have to occur in one of the EJs because it's an increasing chain. So I'll just pick J big enough that has all these finitely many coefficients and all these BIs through Bn. This EJ is a finite field. And since it has all the coefficients of the PI, anytime we take inputs from EJ, and then we hit them with the coefficients, add, multiply, we'll land back in EJ. So this polynomial map P, consisting of P1 through Pn, actually will send EJ to the n back to EJ to the n. Well, P was an injective function. And EJ was finite, so EJ to the n is finite. You've got an injective function from a finite set back to itself. It has to be surjective, right? If I start off with 10 elements and I send them back to that set of 10 elements, and I'm injective, they all have to go to different places, so they go to all 10 places. So that means P maps EJ to the n onto EJ to the n. And since I had my target was in EJ to the n, and P is injective, P is surjective, that means there was some input in EJ to the n that satisfied the conditions. And this is all happening inside CP to the n, so I've shown that CP to the n would satisfy this formula. And so CP to the n satisfies T prime, and by compactness, T itself is true. That's it.
Any questions?
Yeah.
Why is it called the compactness theorem? Is it because you're picking finite things out of an infinite thing, or is it more precise than that?
It is more precise. So if you consider all possible formulas in your setting, okay, those actually, some of those formulas imply other formulas, right? And so you actually get a topology on the formulas based on implication. And that topology is compact.
And is the compactness of that topology related to the theorem?
Yes. I mean, it is basically
But
saying that that
it's saying
topology
it's-
is compact
okay.
is the compactness theorem.
It's fine. Yeah.
It's called the stone topology. Yes.
Any further reading recommendations?
I mean, definitely,
Anderson?
if you like, so there's Hodges. I would say a shorter introduction. So he had a really big book called Intro to Model Theory, and then he did a shorter introduction to model theory. So that's definitely a good book. It's pretty modern as well, and it's statements. In terms of logic applied to combinatorics or logic applied to algebra, I don't have, like, it depends what your interests are. I don't have.
Just logic in general.
Yeah, I would say this one.
So in this context of model theory, are you allowed statements like for all xk in S, right, then some statement, right?
Right.
Are you able to negate statements like that?
Yeah. I
Okay,
mean, well, so I mean, if you negate it, you just get an existential. So
right, but then my concern, when you negate that, you get a statement which is made over all of the set. So sometimes, like, I'm thinking, like, from a anomalous point of view, negating sentences like that can be difficult because, you know, they would say you can only negate it for a specific K, because to negate it would be to treat it as an entire set.
oh, so you're
which you said
saying
we weren't supposed to do.
right? So you were letting the K vary.
Right.
Okay, yes. So that is not allowed. Yes.
Okay.
Yes. So the workaround that I had in the beginning is only if your for all natural numbers appears at the very outside of the formula. It will not work
Right.
inside the formula. Like if you have got other quantifiers or other things, will not work for that. It will not work for infinite. There exists as well, where there exists a natural number. So it will not work for that. So it's all this trick only applies if you've got formulas for all natural numbers on the outside and then a statement. You could split that up into infinitely many formulas, one for each end.
It occurred to me, when you did that proof where you showed there was a model for all t prime, and so therefore there's a model for t, how do you know C is such a model?
Perfect. I was hoping someone would ask that question.
I realized.
Yeah. So this is a hole in my proof that I presented to you. I skipped over something, right? So compactness said I've got these statements T, right? And compactness, we showed that every subset T prime of T had a model, and by compactness that means T has a model. It does not say that model has to be the complex numbers. It could be some other really weird field. Okay. But there are two other theorems that we can use here. One is another theorem from logic. It's called the Lowenheim-Skolem theorem. It says if I've got a set T of formulas and it's got an infinite model, okay, then it has a model of every infinite cardinality. Okay, so I found a model of T. Lowenheim-Skolem says, oh, now I can find a model of T that has cardinality of the continuum. Okay, same cardinality as the reals or the complex numbers. At that point, we use Steinnitz's theorem, which says up to isomorphism, the complex numbers are the only algebraically closed field of characteristic zero that has cardinality of the continuum. So whatever that model was, it actually has to be isomorphic to the complex numbers. Yeah. So it is true, and that uniqueness up to isomorphism is what makes this particular proof work. If there were multiple models, then we'd have some trouble. We just show that the theory is consistent, it has some model, doesn't have to be the specific model that we're looking at. Good question.
Good for somebody, nice catch.
So I think you showed like two big theorems. Were there any other big theorems you considered talking about?
I mean, so there's like various things that you can do with compactness. And I wanted things that people potentially who hadn't seen a lot of different kinds of math would be able to understand. So I mean, some theorems, there's like constructions of groups called, I think, Janssen groups, which are groups where it's an infinite group, and yeah, it's like some funny thing about the subgroups, like what sizes you're allowed to have in subgroups and stuff like that. And it's like, it's a really weird construction. It doesn't seem like something you'd see in a group theory course at all. So yeah, there's lots of interesting constructions that you can do. Basically, another thing I did consider doing is a model of non-standard arithmetic. So if you take your axioms to be just the axioms for addition and multiplication from the natural numbers, you can show that actually there are models, infinite models of that, where you have an infinite prime. And then you also have a new number that has all the original natural numbers as factors. So those are kind of weird things that you do. But I felt like, okay, I construct something weird, but it doesn't have necessarily practical application, whereas this actually does. So I opted for this. Yeah.
Oh, so these are the only two proofs that are known for these two theorems?
No, well, I mean, so the finite Ramsey theorem has a combinatorial proof.
Oh.
And if you look at the Wikipedia page, or there's a proof wiki, I think, that does it. It's an induction proof. It's a little complicated, but it's not too bad. But axis theorem, there's this logic proof, and then there are some more complicated theorem, like proofs of it using analysis or algebraic geometry. But this one's basic. Like this one's like a lot. I mean, it does use Lowenheim's golem, and it does use compactness, and it does use Steinhaus's theorem. But
So in this was like shortcuts for this theorem, right?
I mean, so I think Axe proved it, I believe, with compactness, and I think Grothendieck in his proof also essentially used compactness there. I mean, I believe also did this, like, oh, this statement can be turned into something where we have characteristic P.
Any others? Well, let's thank Dr. Baginski. Some of you may know we've got a conference tomorrow. I hope that some of you might be interested in showing up in. Apparently, content IDs work for this. We'll see. But anyway, it should be a lot of fun. Stay tuned for next week, because next week is right before spring break and it's Pi Day. And guess what? Neil Calkin, of course, will show up to astound us with his mathematical prestidigitations. So, thanks a lot.